This video is about the recursive mathematics of war and what happens when armies of equal qualitative capability engaged on the same territory and fight to the death. What we are doing here is studying the power of simple recursive functions to model interesting real-life situations. Generally, in military exercises, one army is called red and the other blue, so we'll follow this tradition. Here we have 7 blue soldiers versus 4 red blazing away at each other. How does this turn out? After each unit time, attrition on both sides has worn away the numbers. Here's how we might imagine this fight to go. So at the end, 3 blue soldiers are left standing. The result is a simple subtraction of red from blue. Is this how it works? Let's use recursion to figure it out. One way of testing this is to construct a recursive function that simulates this sort of combat. We'll assume that the attrition rate is such that after the end of each unit time, 1 in 10 of the soldiers in either army has scored a kill on the other side. When one army has been reduced to a non-positive number, the computation is over and the numbers of the remaining army are returned. Of course, the bigger army will win, but what we are interested in is by how much. Here is the function coded in Shen. The function is called fight. We've chosen to provide the type of this function, though types are optional in Shen. The first 2 rules are simple. If either army has been reduced in size to a non-positive number, we return the size of the other force. The last line is the recursive step. What we are doing is simulating the continuous fighting by gauging the effects of attrition and feeding the survivors back into the fight. To do this, we multiply each side by 0.1 and we subtract the result from the opposite side. So the remaining red army is diminished by an amount equal to 1/10 of the blue army, and the blue army is diminished by an amount equal to 1/10 of the red army. Well, we're not much interested in fractions of a soldier, so we'll round the results, but we round downwards to make sure our computation ends with 0 or less, and so we use floor. Let's try it out. Our experiment shows that our simple subtraction model does not seem to fit the results we are getting. Let's experiment by having a group A of 50 fight 5 groups of 10 in succession. We'll do this using local assignments in Shen. We call our initial group A and set it to 50. A then fights a group of 10, leaving a force B, which fights another group of 10, leaving a force C, and so on. And we continue until we reach a force F, and force F, the number in force F, is then returned. By the subtraction model, force F should be 0. But actually, you guessed it, it is not. However, if we concentrate the opposing forces into one group of 50, the result is mutual annihilation. What this shows is that if we take a force and divide it into packets, we lose the value of concentration of force, and we open ourselves to what we can call defeat in detail. If we want to observe the effects of defeat in detail, it helps to be able to do so easily without constructing long assignment statements. So here is a recursive function called fight battles, which does just that. Fight battles uses lists which you learnt in earlier modules. The successive armies are held as a list of numbers. Each army is pitted against blue in turn, and the reduced blue army is thrown against the next army. The process ends either with the destruction of blue, or a point is reached where there are no more armies left to fight, in which case blue is returned. Let's try it out. That's interesting. Our smaller blue army has defeated a series of armies which are cumulatively larger than blue. Our analysis shows it is possible for a smaller force to defeat a much larger one if the larger force can be maneuvered into engaging in detail rather than en masse. The mathematics of this was worked out just over 100 years ago by a mathematician called Lanchester, who used calculus to do it, the computers being obviously in short supply. The result is called Lanchester's square law, and it says that the effectiveness of a force in a projectile war is proportional to the square of its numbers. Now this was actually something that was understood long before Lanchester did his work. In the Battle of Jutland, 1915, a great naval battle between the British Grand Fleet and the German High Seas Fleet, Admiral Scheer, the German commander, endeavoured to split the Grand Fleet into two and engage the two parts separately. And he nearly succeeded. Admiral beat his detachment, narrowly avoided being decoyed into a trap, and had to flee 50 miles, chased by the Germans. In World War II, Montgomery criticised the British tactic of scattering armour in what he called penny packets, and used concentration of force in El Alamein to break Rommel's army. Artillery barrages like these were familiar in the Eastern Front. As Stalin remarked, quantity has a quality all of its own.
All through that night and into the broad light of day, British guns poured tons of shells at Rommel's Invincibles, and tough fighters though they are.
Does this mean that in war the largest massed force always wins? Of course not. Our reasoning is based on a wireframe model in which the two sides are equal in all respects. But a smaller force has defeated a larger force where the firepower, attrition rate that is, of the smaller force is considerably greater than the other side. A paradigm is the Battle of Rorke's Drift, where a company of British soldiers, armed with Martini Henry single-shot rifles, held off several thousand Zulus, armed largely with stabbing spears. Our fight function treats the attrition rate as constant, 0.1 for both sides. However, we could instead choose to enter these attrition rates as a parameter to be input to the fight function, a process called parameterization in computer science. We could then simulate the confrontation of forces which were technologically disparate. But I'm not going to spoil your fun by doing that, but I'll leave it to you to download Shen and try for yourself. Now, A last word now on a contemporary event, which is the war in Ukraine, a subject which has taken up a large amount of column inches in the last few months. It is important to see that the principles of combat that we have studied here are in active application right now in the Ukraine, particularly in respect of the Russian conduct of operations. Let's go back in time to March 2022 when the war map looked like this. At this time the Russians had invaded from 3 directions and the focus was on the north where a sizable Russian force had accumulated. The effect of this force was to draw out a lot of Ukrainian manpower to protect Kiev. It's not clear whether the Russians intended to take Kiev or more likely to bring the Ukrainians to the negotiating table. Whatever the truth, the Russian presence near Kiev acted as a fixing operation. That is to say, it drew a sizable force to act as a deterrent to attack. And you can think of a fixing operation like a feint or a jab in boxing, which sets up the opponent for a serious punch. Now this war map was to radically change when the Russians withdrew from the north. But prior to withdrawing and after, the Russians mounted a massive attack on the Ukrainian logistical system. In particular, transport, railways and bridges and ammunition dumps. And the effect of this was to make it difficult for the Ukrainians to reinforce areas under attack. Then subsequently the Russians withdrew from many positions in the north and concentrated their forces in the south and particularly the east. We don't know the exact size of the Russian forces engaged in the Ukraine, but the quote is from 150 to 250,000 men, not vastly different from the 200,000 men credited to the Ukrainian army at the start of hostilities. However, as we've learnt from our model, equivalence in size to the enemy means little when the disposition of the troops is unfavourable. By concentrating their force in the Donbass, depriving the Ukrainians of mobility and delivering the big punch there, the Russians open the door to defeating Ukraine in detail. The Ukrainian counterattacks can be seen as a way of drawing away this concentration of power, but these attempts have made little difference to the mathematics of this conflict. The Ukrainian war has 2 dimensions, space and time. I've talked about the spatial distribution of these forces, but I also want to include time. There has been an attempt by the West to bolster the Ukrainian forces with a miscellany of weaponry, some perhaps rather past their sell-by date. However, these weapon systems are fed by dribs and drabs to the front, and the observations we've made about defeat in detail still hold good. If a large body of trained men and equipment were to arrive en masse, then this might indeed change the course of the war. But the piecemeal reinforcements suggest that Lanchester's law will continue to ensure that these forces are consumed very shortly after they arrive, which seems in fact to be happening. So, will the Russian divide and conquer strategy work? Well, I'm not going to issue a prediction. I'll just say that time will tell. Well, I hope you found that interesting, the modelling of conflict through recursive equations. Do subscribe as I produce more Shen videos, and keep our work going by donation to the Shen project page using the donations page link. I do hope you've enjoyed this presentation.